In the chromatography experiment, we are using a technique simply called chromatography to take a mixture and separate it into its component parts and identify what those component parts are. So chromatography is a technique that separates a mixture into its parts and identifies what they are. In the mixture that we're working with today, we have three possible amino acids: aspartic acid, leucine, and threonine. These are the components of, and many other amino acids are the components of our proteins. All amino acids have the H2N CH double bond O OH part. That's what's shown in figure 1 in bold. Notice they all three have that part. They differ in the side chain, the unbolded part in figure 1. The side chains cause the amino acids to have differences in polarity, and this is the property that allows them to be separated by chromatography. In paper chromatography, a mixture is spotted on a piece of paper. So that's done where we see all the A's and B's. So we have a mixture of component A and component B, and I'm referring to figure 2. Then the edge of the filter paper is immersed in a jar containing solvent. As the solvent rises up the paper, it may carry the components of the mixture at different rates. If a separation occurs, it is mostly due to different strengths of attraction to the filter paper. If a component is strongly attracted to the paper, it will spend most of its time attracted to the paper and very little time in the solvent. We see that in the third diagram in figure 2. We see that A was more attracted to the paper than B. B moved pretty much just with the solvent. A moved slowly as the solvent moved more quickly up the paper because it was attracted to the paper. A component with weak attractions will spend little time attached to the paper and move with the solvent more quickly. That's what B does. So A was more attracted to the paper, B was more attracted to the solvent. Components are attracted to the filter paper through intermolecular forces. Paper is primarily made of cellulose, which has many OH groups. Therefore, a component which is capable of hydrogen bonding to the filter paper will have stronger intermolecular forces with the paper and will move slowly during the chromatography experiment. So that's shown in the left on figure 3. So we're seeing the OH bonds of the chemical cellulose making up the filter paper. And if we have a component on it, like in our diagram figure 2, component A, then it's got more attraction to the filter paper, probably through hydrogen bonding. So it's forming hydrogen bonds with the filter paper, and therefore the solvent isn't pulling it along strongly. A component which is capable of only which is capable of only London dispersion forces, LDFs, like what's shown on the right in figure 3, it will have weaker intermolecular forces with the paper and will move quickly during the chromatography. It will move with the solvent. The solvent is mostly nonpolar, the paper is mostly polar. So the more polar is the component, the less high it rises on the filter paper. Okay, the molar masses of the amino acids are similar. We see they range from 119 to 133 grams per mole. So hydrogen bonding, whichever has the strongest, will be expected to rise the least. The one with the most London dispersion forces will rise the most. So we will be making calculations from our chromatography experiment, and let's see, have we seen what the actual paper, okay. Figure 5 shows the paper that we will set up in the experiment. So in our unknown, we can have aspartic acid, leucine, and or threonine. So we can have all three of those amino acids or just one of them. Now, in order that, okay, so the chromatography will separate them into their components because those three have different polarities. And then to identify which are in our unknown, we will run simultaneously a known solution of aspartic acid to see how far up it rises, a solution of leucine to see how far up it rises, a solution of threonine to see how far it rises. Just to see how the spots look when we have a mixture, we're going to also prepare a mixture of aspartic acid, leucine, and threonine. That is what's referred to here as all. And we will put that on the all spot. At the aspartic acid spot, the leucine spot, the threonine spot, we will have just the pure substances. And then where we have unknown twice, we will spot it with our unknown doing 2 runs. We're using the same unknown, just running it twice. So we're putting our spots there. We're putting this paper, making a cylinder of it, putting it into a jar containing solvent, and we're giving it about an hour to run. That's about how long it will take for the solvent to rise up about 7 centimeters. At that point, our unknown should have several spots in it. The all should have all 3 spots, and the aspartic acid, the leucine, the threonine, each of those will have just 1 spot. The heights of those will vary. We will then quantify our observations. So we will take our paper out, we will spray it with ninhydrin, which brings out the spots, and we will let it dry, and we will then measure distances. We will measure the height of the solvent, that's referred to in figure 2, or rather figure 4, as L, and we will measure the heights to the middle of each spot, that's referred to as D. For each spot, we will calculate RF. That is the distance the component has moved, D, divided by the distance the solvent has moved, L. So we will determine that for each spot. In the pure solutions, in the unknown, in the all solution, and in the unknown solution. So here figure 7 is showing the filter paper that's been rolled into a cylinder and put into the jar. And here's the steps involved in making the measurements. We can skip the pre-lab as usual and go straight into the report. Okay, so in the experiment video, I will give you the, unknown letter. We will only have one unknown the whole class will work with. And I will show you the chromatography paper as I'm preparing it and when it's done. When it's done, we will draw a line to where the solvent moved to. Once the paper's dry, it's a little hard to see that line, so I'll draw it when it's still wet. And then once it's dried, we will measure the height of spot 1, 2, 3 of the 3 spots at position 4, that's the all. And then for the unknown, the 2 runs, we will measure the heights of those. You will then calculate RF, so it will be the distance the amino acid moved divided by the distance the solvent moved. And from that, you should be able to identify what's in the all solution and what's in the unknown solution. And then there's a few questions as to looking at the structure of the amino acids, which is the least polar. So look to that side chain, the non-bolded part in the amino acid to decide, and which would be the most polar. So look to the side chains to decide that, and then based on your results, the RF values, the one with the smallest RS value, that must indicate whether least or most, and so on. So answer those questions. And then question 4 is we're given 2 other amino acids, and you're asked to predict which would travel the furthest, which is the least polar. Alrighty, so check over your report, make sure you're happy with it, and then scan it, prepare it as a PDF file, and submit it.